How many people here are involved in some kind of enterprise AI effort today? Okay, that explains it. I'd love to talk to you about your own experiences as well. I want to share mine today, what I've learned in the last 2 years. So this is a photo from 2 years ago. This was in Beijing. It was coincidentally the first O'Reilly conference in China, in Beijing. And I gave a keynote that was entitled Innovation from China, what it means for machine intelligence and AI. It was about how China has a lot of data and was very, very aggressive. At the time, it was not obvious about investing into AI. And of course, today, a lot of that is obvious. What I didn't know at the time, at that time, is that 2 years later, I would be here at the first O'Reilly AI conference in London. And in particular, it'd be a totally different role. 2 years ago, I was the CEO of a startup called Arimo. We were funded by Andreessen Horowitz, and we were working on enterprise machine learning, big data. And
it's being recorded.
Shall I start over?
No, it should be fine.
Okay.
Do you want to put that in your pocket?
All right. So what I didn't know at the time is that I would be here speaking in a slightly different capacity today as part of a global conglomerate known as Panasonic, and talking about my experience over the last 2 years leading teams at Panasonic. We're still known as Arimo, but our task within the large corporation is about implementing AI for the company. I want to give you sort of a perspective of how we got here. So to understand the path that we've taken and the journey that I've taken in the last couple of years, we can go back to 100 years ago when Panasonic was first founded by this gentleman named Matsushita. Right? I think some of you may actually know a company called Matsushita and actually what became Panasonic. And he started the company with a simple but I think very profound vision, right, to make life better. It was the beginning of electricity, right, electrification of the world, and he wanted to make things like essentially the light bulb receptacles. And that was very advanced technology at the time. Now you fast forward 100 years later, this October, Panasonic is celebrating its 100-year anniversary. Right? So that'll be in Tokyo. And it is now a global conglomerate with a dizzying array of products. And I think many of us are familiar with the consumer product line, TVs, VCRs, air conditioning, and so on. Perhaps we're less familiar with the commercial side of it, commercial air conditioning, HVAC, ventilation, and so on. And then also things like factory automation, smart city. And how many people know that all the Tesla batteries are actually made by Panasonic? Right? Wow, okay, so now you learned something new. Tesla actually does not make those cells. So Panasonic does all of that battery work at the Gigafactory, and Tesla does the assembly into the battery units. And most of us probably flew here to this conference, so there's a 70% chance that you use the in-flight entertainment system or the Wi-Fi that is provided by Panasonic Avionics. So it is today a very large global company with a wide range of products and services, and is very proud to call itself Panasonic because it's also one of the world's top brands, best global brands to 2018, the top 100 brands by Interbrand. Well, with size and age also comes a challenge. So the gentleman, the CEO, Tsuga-san, took charge of Panasonic about 6 years ago. And he had to essentially, that was a turnaround effort. And now it becomes the challenge of how to reignite growth at this large $70 billion engine. Okay? And so the challenge there is to capture the, I choose these words very carefully, capture the global economy of scale. Now that may sound very counterintuitive, right? It's already a global company. What about, what's the challenge with capturing this global scale economy? Well, I've also spent time at Google. I was the engineering director there about 10 years ago. And at Google, companies like Google and Facebook and Amazon and so on, the company grew up in the internet age, and it knows nothing but scale, right? So infrastructures and so on are already horizontal across the entire company. And so let's say you have a team of 5, 6, 10 engineers building an interesting internal product. And if it works well, it's available to all 70,000, 100,000 of your employees the very next day. That is not the case at companies like Panasonic, right? It is essentially a conglomerate collection of vertical companies that in themselves are doing well as businesses, but there can be a lot of duplication and there can be overlaps. And internally, when you deploy infrastructure for one unit to use, that may actually not be accessible to another one or even duplicated. So how to capture that efficiency, that agility, and really the organizational intelligence for the 21st century is one key goal for Panasonic today. Of course, all of us are familiar with this phrase by Mark Andreessen, software is eating the world, right? And Panasonic, like a lot of other companies, are traditionally hardware, right? And it does recognize that a greater and greater part of the value creation is actually not the hardware itself, right? Not just controlled by software, right? But the value creation, the consumer, the relationship with the customer, the consumer, the businesses, is all coming from software. So the CTO of Panasonic, Miyabe-san, set out in this course in the last 5 years to essentially help build horizontal infrastructures across Panasonic. And a key layer, of course, a technology of our times is artificial intelligence, right? And artificial intelligence applied particularly to IoT, right? All of the products and services that I showed you earlier have a very core element of it, the concept of Internet of Things, and in particular, industrial IoT as well. So in that context, Panasonic set out to essentially look at the market and say, acquire a leading AI company. And it turns out 2 years ago, I didn't know that, but the story continues, and one thing leads to another. We started out with the first POC with Panasonic in June of 2016, was very successful, and I'll share with you that story and how it evolved and what I've learned since then. But we have two key missions at Panasonic as Arimo, 100% owned subsidiary, is that number one is to build AI into the range of products and services that it has globally, and number two, to implement an internal AI platform for Panasonic engineers worldwide to use. So today we're going to focus on the first part, the build AI into products, and what I've learned since then. So if you look at what we've done here is anomaly detection. It's a proprietary technique, but the concept of anomaly detection is, I'm sure, generally known. The proprietary technique that we developed. What you see here is what we have implemented, that over time, you see that sensor data coming into the system, right? And we have an algorithm that's sitting there observing all this data, and then it will see patterns over time, right? And so it can encode this into lower dimensional space, and essentially here you have this donut shape. Each of these points is a time series, right? So if you have a sensor that is, reading pressure or temperature and a range of them, right? High dimensions, you've got, hundreds or thousands of sensors that encodes over time into a single point. And over time, you can see patterns of these data points and also relationship among these sensors, and they tend to form these patterns. And anything that comes in that doesn't follow these patterns can become outliers, right? And so you can do density estimation and say, okay, for a new data point that is coming in, what is the likelihood that it belongs to the distribution of the data point that I have seen? And so you have a very clean signal here, right? This is called the reconstruction probability. How likely is it that I can reconstruct the data? When it drops, then you have an anomaly, right? And many of these cases, the anomaly indicates an impending failure. 2 weeks from now, that pressure anomaly or that divergence between those two sensors will result in a compressor failing. So then you can schedule maintenance and you can say, well, go fix it before there's a much more massive downtime that is much more expensive. So in techniques like that we apply, and I want to share with you among the many use cases that we have worked on, a couple of examples. All right. One is energy optimization. A key customer base of Panasonic on the industrial side is supermarkets. Right? Supermarkets in Japan, but also worldwide. It acquired a company in the US called Husman, and then also has operations in Oceania. So today, Panasonic has a leading share of that market that we call cold chain, right? At the end of that cold chains, you start out with like fish being caught, and then it sort of goes all the way to the supermarkets. And so you got to keep that fish or that vegetable fresh, but then you want to do it with the minimum amount of energy consumed. So the way that's been done typically is that the system would be installed, and then there are sensors that are monitoring pressure, temperature, load, even ambient temperatures, conditions, and so on. And then 2-3 weeks later, an expert engineer would come, and what they would do is collect all that information, look at essentially the behavior of the system, the load of that particular system over time, and using some kind of life skills expertise, including some science and some art, come up with a bunch of settings on the dials to optimize that system for that situation, right? And the typical savings, energy saving between a tuned system and an untuned system is about 3%, right? Now 3% sounds like a small number, but that turns out to be about $300 million per year in terms of energy consumption in supermarkets across Japan that are customers of Panasonic. So what we did, the problem statement that was posed to us, that first POC that we did with Panasonic back in 2006 was that there was data that was prepared. The problem statement was very well articulated and said, can you look at all of the massive data that we have today, right? And look at the history of all the settings by the experts that we have. Can you build a model to automate that process, right? And it turns out we were able to do that in just a 2-week POC with very high accuracy. And it turns out to be a bake-off, and we won that bake-off. And so today, what Panasonic is doing is in the process of rolling this out. And the interesting thing is that since you can now automate that human expert, you can do that not just once a year, you can do that not just once upon installation, but you can do that once every month. And when the optimization is done once a month, you can optimize it for summer, for fall, for spring, and so on. So before, the expert was actually essentially changing the settings so that it would essentially work through all the season. But if you optimize it every month, then the savings become not just 3%, but 15%. So the impact upon rollout is 1.5 billion of energy savings, and we estimate about 10 tons of CO2 saved from the atmosphere every year. So that's a very high impact project. Let's shift to predictive maintenance as a second major set of use cases. And it turns out we're able to use the same sensor data that is coming off of the same set of equipment, and using the technique, anomaly detection technique that I described to you earlier, we're able to see in advance, right, many of the failures of these refrigeration systems. For example, compressor failure or clock filters and so on, right? And the savings there is if you have a supermarket or you have a manufacturing plant and it goes down. So for example, there have been estimates in the US that the average manufacturing plant, every minute of unplanned downtime is about $20,000, right? That's way, way more than a trip, one truck roll of somebody, an engineer going out and fixing something in advance. So you can reduce the expensive unplanned downtime. You can also improve the maintenance scheduling. It's no longer, on demand, but you can say, okay, I think something is wrong and we're gonna go out. Within the next 2 weeks, I can schedule all of my engineer times. And it also enabled new service models. So Panasonic also provide this maintenance service, right? Shifting from the CapEx model, instead of selling equipment to customers, it's selling cooling capabilities. So that maintenance is also part of that OpEx service. So enable this new service model and it gets new revenues from that. Okay, so let's follow the predictive maintenance example and see how far we get in terms of what we have learned since then. Okay, so we're in London. This is the former image of the former Prime Minister, Margaret Thatcher. If you know what this is about, don't spoil it for other people. But how many people think these images are more similar? And how many people think they're very, very different? How many people think they're pretty similar? Okay, how about those that think they're very, very different? Okay, about 50-50. So I'm gonna flip it over and show you what it actually is. Okay, so why is that, right? Now if I flip it back, you can now sort of, even if you know that, you can still see there's a difference in your perception, right? It's very hard to tell the difference between these two images, whereas this one is completely different, right? So from the anomaly detection perspective, the image that I showed you earlier is that, so this shows both the strength and advantage and weaknesses of our perception system. So our brain, very similar to the algorithm that we've trained, they reduced the high complexity, there's a very high dimension, lots and lots of pixels, into familiar patterns of images, in this case that we've seen a lot, right? And so when you see images like this, you're actually not seeing every pixel. You're actually very rapidly compressing the dimensions, and you're saying, okay, I've seen this pattern, and this is very, very different. So what that says is that we can be very efficient at recognizing anomalies, differences, but it also means that we're now sort of the victim of the patterns of things we have seen before. So we can only tell that something is different or abnormal based on the data that's been given to us. No more, no less, right? So based on that, we're going to go deeper and say, okay, anomaly detection-based predictive maintenance and follow that specifically. One key lesson that we learned, right, in a sense, has nothing to do with AI. It means that when we're generating these new signals, right, I mentioned earlier that when we see an anomaly happening, right, then we say, well, something is about to happen. We may not know what it is. We may be able to say, it's probably a compressor failure that's going to fail in 2 weeks, with 70% probability. Or we may say that something is very different from normal operation. You better go take a look. Now, the thing that when we set out on this, we didn't think about, but when we actually roll it out to market, we realized this is a completely different information for the entire service staff, right? Before, when they get a call in, people, the customer would say, well, it's not working, and there's an alarm code, A65. They look up in the book, A65 is probably a compressor, prepare all of that. Now this is a very new signal that says something is wrong, right? What is a maintenance engineer supposed to do? So the thing that we have to learn is that it's one thing to be collecting data and building models. It's quite another when you roll it out to the field and say, okay, now we're going to actually give you more work to do, right? Right. So people can say, I thought AI was supposed to save me time. Why are you creating new work for me? Well, hopefully over time, we're creating this new workflow, but we're reducing a lot of the unnecessary workflow later on. So we've developed this whole framework called the Predictive Maintenance Framework, right? And the key here is this decision box here, right? If you sit there and imagine what predictive maintenance can be, in the ideal case, you realize you don't think of this decision box. And that is that in the ideal case, you see this signal coming and you say, okay, I know that that's a compressor failure that's going to come in 2 weeks from now, so go do something about it. In the real world, right, even with a company like Panasonic, the cold chain use case, where there's data that's been collected for the last 5-10 years, the labels, the targets that to identify a particular set of signals indicating what the impending failure may be, the failure list, right, the maintenance records can be very sparse, number one, not very well kept, number two, right, and actually quite wrong a lot of times. So we're not actually able, in the first instance, to go take the data and build this beautiful model that says 2 weeks from now, this is the cause of the problem you will see. So we actually have to back up and say, well, we cannot build, in the machine learning sense, a classification model. We can build an unsupervised model called anomaly detection. So we can tell you something is wrong. And maybe with luck, with better data, we can tell you that it's likely to be this with 80% probability and 20% probability here and there. But in many cases, it's just something is wrong, right? So you have to make, essentially, when you roll out to the field, you're creating this eventual workflow. There's workflow from day 1, there's workflow day 60, there's workflow day 365. And workflow from day 1 says that you're going to get a signal, and that signal is not going to tell you exactly what to do. So you have to go and diagnose the system, find and determine what's wrong, and then go fix it. But after you've done that, you, meaning here this maintenance engineer, would then go back, right, and essentially say, okay, now I'm going to label that. I'm going to say, okay, I know what's wrong now. That signal then goes back and feed it into the system, the learning system, as additional labels. So it turns out the phases where you're saying collecting data, training, building the model, and rolling it out is actually all integrated, right? Even when it's out in the field today, we're still in the process of collecting more data and learning. And that's, in sort of a detailed sense, how the system, quote unquote, gets smarter over time, right? So a very closely related lesson there is do not blindly believe ground truth, right? So in school, we're giving this data set. We say, okay, here's, like, for example, ImageNet, all nicely labeled. All you have to do is build the best model possible, right, to get the best percentage response, okay? Well, let me give you an example. And this example is the rule rather than the exception. So using the same technique, we take a different data set, right? In this case, it's manufacturing data, and essentially also time series. And we have labels, and the labels are colored. We can ignore the green, but essentially the blue and the red there. So you can see the behavior of the system, mostly blue there, and maybe some red that fall in there that we can't really tell apart. But on the upper cluster there, you see that there's a lot more red, and yet we still can't tell it apart from the blue. So the instinct of a data scientist is going to go say, well, I'm going to try different techniques. I'm going to try, different degrees of. So I'm going to try, essentially, if it's not deep learning, then it's going to be SVMs and so on. I'm going to try different kernels, and maybe I can separate it in higher dimensions, and then I can tell the data apart much more easily. Well, it turns out one of our data scientists was looking at the data more carefully and say, you know what, this looks exactly, like this time series looks very similar to another one, and yet the failure that comes down, a month, 2 months later are very different. So why is that? So essentially, we went back and we looked at all the labels that were given to us, right? The labels in this case, again, the failure cases, and we found that it's a huge mess, right? It's not even funny. So the idea there is that you can have alarms that happen on these manufacturing, on the manufacturing line, that can be very removed from the maintenance events that happen. Some of those events are scheduled events. So people will go in and I'm just going to replace this component no matter what. That has nothing to do with the alarm that happened upstream. And so that sounds trivial, but when you're dealing with lots of these data sets and you don't spend a lot of time sort of questioning everything and then going back and say, I don't believe the labels, then you end up spending a lot of time as data scientists trying to build better and better models against very poor data. So after we've done that, then you get something like this, right? So it turns out the model was quite good enough. Just go work on the data, okay? And that's a recurrent pattern that I think as you work on these things, you hear a lot. Another lesson that we learned is that, so I gave you the example of a division in Panasonic called the Appliance Division, AP, that was highly organized. It had good sponsorship. It had data ready and so on. But we also run across a lot of situations where people say, I really want the power of AI to transform my product and my service. Now, my customer is very sensitive about their data. So typically in software projects and so on, you say, well, let's do a little bit, right? And then prove the value. And then once you prove the value, do a little bit more. The problem is in machine learning, there's no such thing as a little bit of data giving you a little bit of value, right? So this is something that we have as part of the evangelization, have to tell people, you have to make a clear commitment to collecting and providing the data before any of this can be meaningful. There's no such thing as getting a little bit of AI out of a little bit of data. So the corollary that we tell people is, yes, collect and save all that data already. I remember back in 2007 when I was running Gmail, it was quite what I thought was quite a crazy, but it turns out to be a courageous decision to actually save all of the logs. You can imagine how much log data that would have been. And that data was not really being used for any purpose at that time. But Google made the decision to say, let's just save it. It'll be useful at some point. And of course, sure enough, that is now very powerfully, enabling a lot of use cases at Gmail. So collect and save that data already. Okay, so in the remaining few lessons, I want to share with you something that some of you may be familiar with, but I want to reiterate. This is machine learning and software engineering can be very, very different. Right? Now, some people like to say that it's all software engineering with two different branches. That's okay too. There's just different taxonomies. But the one thing to keep in mind is that there is something very different about this. And Peter Norvig cites a few of these things. You know, he talks about the uncertainty of objective. What is it that you're trying to do? It can be often unclear, or it can be often changing in machine learning or AI projects. And what you recommend to do, the action can be very, very different. And that's, so what we find is that in software, essentially you write a program and you provide it with inputs, and what comes out is the output. Very straightforward, right? In a very real sense, in machine learning, you're giving it the input and the desired output, and the training process produces a program, okay? And that has very important implications as to what processes are involved. So what we find, right? So the industry has a bunch of processes. This is ours, right? What we find is that the key that the essence that I'd like you to draw out of this is look at all the arrows pointing backward, right? Now, you don't see this in normal software engineering projects that I've led, right? They typically, you know, flow in one direction unless something is very seriously wrong, and then you go back. In AI, enterprise AI, going back is very normal. I'll give you a few examples of why you go back. You're giving some initial data set. That's good for building models, but that's for just building feasibility, right? Is this data set predictive of the question that we're asking, right? And if the answer is no, then you go back, right? Say, collect more data. Sometimes you say, well, actually, it's predictive of nothing. But in the process of learning about it, we think these are the better questions to ask, right? And so that you also go back and say, okay, in that case, we'll collect different kinds of data. In the process, business can also change, right? People say, we're building a product, we're talking to some customers. The value that you proposed earlier was interesting, but actually they think about it and they think this would be even a bigger deal in terms of differentiation, for example. So the objective can change. And I think that's what Peter Norvig is talking about, right? The data can grow, it can change. Even if you go through all the way here, new data is coming in, new labels are coming in, and even something as simple as a distribution shift, right, which is sort of a well-known thing in academia, can happen. But you can have actually new equipment, right? Every year you're generating, you're rolling out new models. When I say model here, I mean the equipment model. Let's say a new air conditioner or a new refrigerator. And what you collected last year, what the model you built last year, has nothing to do with it, right? So that can change. So the project, quote unquote, what we think of in software is regression, but here I want to call it iteration, is really the rule and not the exception. So this is a fact of life in terms of, you know, building AI projects in the enterprise. And the last set of lessons that we've learned here is, as the story that I told you, I went through it rather quickly, but I want to stress here, is that one of the most successful projects that we have completed and now rolling out to market at Panasonic started out with a key executive commitment, right? And it's a key to success. And so a gentleman named Hama-san is the president of the division, of the appliance division, right? I shared with you earlier how the data was already available, the problem was well formulated, but I think it's also very important that this division in Panasonic made a commitment very early on that the investment in AI, in machine learning, the value of that is not initially going to come from the P&L of that project. It's not like, you know, this is going to make, you know, $2 billion for me a year from now, right? It may make a marginal increase in sales, right? But the most important thing as far as this strategy, when it was defined, is that the differentiation that AI can bring can help that Panasonic division maintain and even increase market share. And so that's a very important strategic determination that allows that budget to be committed, right? And if, you know, many of you probably work in large enterprises, and you can see how you can have a lot of people, but until budget is allocated, nothing happens. And so that's, I think, a major reason for the success of this particular set of projects. And it has additional ROI to that investment. It's not just the P&L. What is the ROI that this particular division has seen, right? Some of the benefits here are, I've just shared with you, product differentiation, right? But also we've seen over the last 2 years, the teams that work with us, not coming from a machine learning background, they're very strong engineers, very strong product people, But now they're also experts at, of course, we're still the machine learning experts, but they're also experts now at understanding what it can and cannot do, at problem formulation. And equally important, not just the engineering side, but on the business side, people no longer come with, sort of empty questions like, oh, I love AI, can you do something for me? It's very well thought out, right? Very well understood in terms of the goals of the business and how AI can play a role in it. So the team maturity has increased exponentially. And that division is seeing what I call increasing returns on AI. In other words, it's becoming much more sophisticated about it. And so it's not just one project now, but it's growing. The number of AI-enabled and AI-profitable project is growing much faster at an increasing rate compared to, say, divisions that haven't made that investment. So with that, I'm going to summarize and then leave room for some questions and answers. So the key enterprise AI lesson that I've learned over the last couple of years are here. One, know that you're creating a new workflow, right? It's not just the modeling part. It's not just the data collection phase. But when you roll it out, you have to take into account what workflow you're creating and how that could feed into the data collection and the model building later. Second is, don't just believe ground truth. I like to say there is no ground truth, right? Show me the data, and then I will become much more familiar with the data over time, and then based on that, I'll believe what the labels are. Third is that there's no such thing as a little bit of data. Collect the data now, right, and save it. And then fourth is plan for a lot of iterations. And another thing that I didn't stress much, but in a different context, when I speak to my team, invest a lot of time in the data understanding. Very often we focus so much on building that model and getting that 98% or 95% accuracy. But when you go back and you look at the data a little bit, it turns out that that 1 minute or that 1 hour invested in understanding and visualizing that data can return many-fold, many dollars saved compared to just spending more hours on making a better model. And then fifth here, executive commitment is key, and the ROI, once that investment is made, can be much more than just the immediate P&L of the project. Okay? So with that, I want to close with a sort of very optimistic statement that you saw from the example of that co-chain energy use case, right? Yes, you can have $1 billion impact if you're very careful and very conscientious about it, and yes, you can save the world. All right, with that, I'll leave room for questions and answers.
You mentioned the changes in workflow that introducing the models had. Could you expand on that a bit more in terms of the investment that's needed to adapt the workflows?
Right, yeah. Great question. You mentioned the word investment. I think that's key because initially, so for this particular situation, it does result in new personnel that have to be essentially. So there's maintenance personnel that's already watching, at central operating NOCs and so on, that are responding to all of these signals that are coming in, these regular alarms. And so now that cannot be, say, well, we're going to replace it with a new AI system, right? That business has to continue, the workflow has to continue. So any new signals that we're sending in has to be handled as additional workload. And so that may mean the same people have to do more stuff, or you got to send in a new team. Now, the commitment is that over time, the processes and the maintenance that result from this new signal will drastically reduce the need for the other workflow. But there has to be at least, let's say, a year of field work where both are going in parallel. So that's an example of the kind of investment commitment that has to be made.
Yeah, and is that the time frame you're thinking of? Has it been a year, and now are you seeing the benefit?
We're a few months into it.
Okay.
Other questions?
I'm interested in these new workflows because often with AI, you hear of it replacing workers or
Yeah.
taking people with skills and making them redundant. And it seems to me that's a very positive thing to bring to a workforce, saying the AI we're bringing in here is not replacing you, it's requiring more from you. And instead of going to another company and just replacing the thing that broke, we're giving you the ability to spot that thing.
Right.
Are you elucidating that message within Panasonic?
Yeah, so there's sort of two sides to that problem, right? The particular use cases that I'm talking about here, there's already a dearth or a scarcity of experts. And in a sense, it's only a scarcity when you look back at it, right? You make do with what you have, and so let's say Panasonic has X number of engineers that can do this sort of expert maintenance, then that's a service they can provide. So the minute that we automate a lot of this, then the value can be provided, as an example that I gave earlier. Instead of doing this once a year, you can do that, every month. So that was something that there was no workforce available to take care of to begin with. Another example in the case of in the U.S., it turns out a lot of this maintenance work is done in the U.S. by people that are sort of go to vocational schools, and they make very good money in this trade. But there's a trend, really a multi-year trend, multi-decade trend in the U.S. where people sort of shy away from that. They all want to go to college and they want to do sort of professional work. So companies like Panasonic are finding it very hard to be able to hire this well-paying expertise, right? Very much like the skills of machining in the U.S. So a lot of that has disappeared, and so I think that's where a lot of the automation that companies like Panasonic is implementing is really solving its own problem about that scarcity and say, how do we scale the current workforce that we can't hire enough, right? And use AI to add to this. And so I think you'll see a lot more of that. We could have more coffee and talk about this impending replacement of the greater workforce as a whole. But I think the pain points that companies are feeling first is that they can't hire enough of this, and how do they provide more of the same or even better service to their customers using AI.
Thanks. I have a question with regard to the success rates, because obviously all pilot projects cannot be successful. Could you tell a bit more from your experience about what are the rates, or what are maybe some of you mentioned the criteria already, but
yeah, that's a good question. I can't give you the exact numbers, obviously, but think of it as like hiring, right? We typically think of the numbers are not as bad, but depending on where you start to count the funnel, right? So, for example, we hire in Silicon Valley, we say, we have less than 1% success rate. Well, that's because you count at the very beginning of the funnel and say, there's resumes that are sort of just flowing in randomly and so on. But among projects that are well thought out and with data that's available and so on, right, the success rate then becomes much higher. Right? It has a chance of going through, and even if the initial formulation isn't there, because the data is there, because there's executive commitment, it actually stands a chance of evolving, over time into something that actually is quite meaningful. So we've had successful projects where the actual, let's say the data science model, the machine learning model, is being built that has very little resemblance to what was imagined in the first place, but is still considered successful because it's really a collaboration between the data science team and the business and engineering team that makes it successful. Right.
Thanks.
Maybe one more question.
Okay.
Okay.
All right. Thank you.